Today, my presentation will be about scalable, learning-based, cooperative spectrum sensing for distributed IoT systems. A little bit about the content of presentation. We will start with a problem statement and go through the concept of multiband spectrum sensing as a potential solution. A distributed model for IoT systems will also be discussed. Then, we will move along with the most important part of the presentation, the proposed scheme entitled Heterogeneous Multiband Multi-User Cooperative Spectrum Sensing, HM2-CSS. To prove the efficiency of HM2-CSS, some selected simulation results will be further illustrated. And finally, some conclusion remarks will be made. Internet of Things leads to an increasing spectrum demand. Unfortunately, spectrum is limited and costly. We're facing several sub-problems, or I would even say challenges, that have to deal with spectrum assignment for IoT. To begin with, static spectrum assignment is almost impossible in the IoT case, and this is because the number of devices in IoT is relatively larger than in conventional networks. What makes it worse, the number of devices in IoT systems increase with time, and hence scalable spectrum assignment solutions are required to accommodate needs of IoT. In addition, IoT devices are heterogeneous in nature, and therefore interoperability of these devices may become an issue, especially if we're talking about distributed networks that have no centralized control. Now, if we leave aside the IoT-related challenges, we're facing spectrum underutilization problem by itself. Studies have shown that statically assigned spectrum is utilized only around 30% of time, and hence most of the time the spectrum is wasted. The key solution to this problem is multiband spectrum sensing. To understand what is multiband spectrum sensing, let's have a look at the figure on the slide. We can see how wideband spectrum owned by legitimate users, also called primary users, is divided into non-overlapping subbands. They are also called channels. In this way, multiband spectrum structure is formed. Here, we can see how primary users are occupying the spectrum only at specific periods of time. Therefore, some channels may become vacant from time to time. By sensing the spectrum, other users can acquire the knowledge of whether the spectrum is occupied by primary users or not, and hence utilize the spectrum when it is not occupied. And in this way, by performing multiband spectrum sensing, secondary users can opportunistically access spectrum without affecting the transmission of primary users. This means that if a primary user appears, the secondary user has to vacate the channel. Now that we had a look at the concept of multiband spectrum sensing and its benefits, let's have a look at the distributed IoT model. Distributed IoT system model can be formed over primary network with specific number of primary users, M, each owning a channel within the wideband spectrum. At any particular period of time, primary users can either be in the idle mode, meaning that the channel is unoccupied, or using its channel. And of course, along with the primary network, we have a secondary network that consists of k heterogeneous secondary IoT users. To give an example, here I consider three types of secondary users based on the detector technology they own: the energy detector, ED, the pilot tone detector, PD, the OFDM-based detector, OD. These secondary users have their own spectrum needs, but do not own any channels, and hence they are willing to cooperatively sense the spectrum and identify unoccupied channels for their use. To determine the availability of channels in the ED case, the received signal power is estimated, and hence ED-based secondary users do not require any prior information about the signal. In the PD case, the orthogonality property between the pilot tone and the data carrying signal is used. And here, the pilot tone of the signal is required in order to sense channels. As for the OD case, and this is the most complex one, using the knowledge of cyclic prefix and the OFDM symbol length, inherent signal correlation incurred by cyclic prefix repetition is taken into consideration. So we can see how different detectors have different capabilities in sensing channels, and hence some of them may require particular information about primary users. In most cases, technical details of primary users are unknown, and only certain significant details may be known at the secondary user side. Primary users can share these details with secondary users through a predefined agreement, and this agreement can allow secondary users to use the shared details to improve primary users' detection over channels and hence reduce the potential interference levels for both primary users and secondary users. Depending on the sensitivity on an IoT application, the level of shared details may also vary, and therefore we consider in our system model heterogeneous information known about primary users, so we can have primary users with technical details of the transmission. And we further assume that only certain information about the primary user transmission is known at the secondary user side. So hence, we define three main channel types considered, and they are with no prior information about the primary user signal, with a known pilot tone of the primary user signal, and the channel with an orthogonal frequency division multiplexing primary user signal being sensed over it, so the OFDM signal. The one that will be sensed by the OD detectors. And to perform scheduling assignment to sense channels, a leader for each channel is selected from secondary users. These leaders then decide on multiple channels to be sensed by each secondary user. Now, due to low complexity of IoT nodes, user is assigned to sense minimum 1 and maximum I channels, where I is less than M. Here a channel arises. How to schedule heterogeneous secondary users to sense multiple channels. Heterogeneous multiband multi-user cooperative spectrum sensing scheme is proposed to solve this problem. So HM2CSS first selects one leader for each channel. Separate optimization problems are proposed for each detector type based on their sensing capabilities and can be integrated into the system in a modular manner and executed concurrently for all channels. And particularly, one module and hence a detector type is selected for each channel based on the information available about it. These leaders are selected as the best secondary users to listen to for the corresponding channels. We then select corresponding cooperative secondary users for all channels concurrently. For interoperability, only secondary users with similar detector type as the leader's detector and owning different sense information can be selected for each channel. And to do so, a unified optimization problem is formulated that maximizes the correlation of the sense signal envelopes with the sensed leader's envelopes through something which is called Kremer-von Mises test. And this is a goodness of these tests where the higher the value is, the lower the correlation is between the values. When the cooperative secondary users are selected, they sense the assigned channels and perform diffusion-based distributed information exchange to make a common decision about channels occupancy. And particularly, information exchange in diffusion learning is done through iterations. Each case secondary user combines a small portion of all other cooperative secondary users' test statistics information with the weighted average of all locally sensed results, where QM is the number of cooperative secondary users for channel M and mu is a learning step size. And finally, when the decision about channels is made, the available channels are used by secondary users with highest priorities, and after a specific period of time T, the process is repeated once again. So in order to demonstrate the efficiency of HM2CSS, some existing distributed schemes are used for comparison purposes. They are a random spectrum sensing strategy, RSSS, and a heterogeneous version of the adaptive spectrum sensing strategy, ASSS. In RSSS, cooperative secondary users that sense multiple channels are chosen arbitrarily, so this means in a random manner. ASSS, on the other hand, uses primary user traffic patterns to determine that determine the channels that to be sensed, so selecting channels to be sensed in an adaptive manner, such that the selected channels are more likely to be unoccupied. And along with this, some centralized schemes are further used for comparison, which are OR, AND, K out of K, and the majority rows. And finally, to make this scenario applicable to IoT, we consider heterogeneous information available about 50 channels with up to 100 secondary users. Let's first have a look at the distributed learning results for the different schemes. On the x-axis, we can see iterations as they pass through time, and on the y-axis, the test statistics is shown. This means that at iteration 0, it represents the locally sensed information, and as we move forward with iterations, the results of learning are illustrated. The main advantage of the proposed HM2CSM scheme shown in figure A over the existing RSSS and ASSS schemes in figures B and C respectively is that it does not select cooperative secondary users with similar locally sensed results. Now, regarding receiving operating characteristics, which is probability of detection versus the probability of false alarm, HM2CSS further outperforms RSSS and ASSS. It is the only scheme that works in the preferable according to the IEEE 802.22 standard, which is the upper left-hand corner block on the figure. In other words, it does have greater than 90% probability of detection for the false alarm probability of 10%. And what is more, we can notice that for each scheme, how performance differs as we increase the number of channels sensed by one secondary user, which is I. For the existing schemes, the higher the value of I is, the better the performance is. However, for the proposed scheme, the results are almost the same when the value of I is greater than 5. So this means that HM2CSS is able to achieve approximately similar performance by selecting less users and hence save some energy. And finally, let's have a look at the receiver operating characteristics comparison with the centralized schemes. Generally, it is well known that centralized schemes outperform distributed in terms of performance due to their centralized control. However, we can notice that the proposed distributed HM2CSS scheme performs in a manner close enough to the centralized OR rule. In this presentation, we briefly went through a diffusion learning-based scheme called HM2CSS for distributed heterogeneous IoT systems. From the distributed learning results, we have seen how HM2CSS provides efficient cooperative secondary user selection to sense multiple channels. Specifically, it avoids selecting secondary users owning similar information about the channel. HM2CSS has further been proved to be scalable in terms of receiver operating characteristics. It outperforms the existing RSSS and ASSS schemes and provides a similar detection performance to the centralized OR rule. This presentation has been based on the recently accepted paper in IEEE Open Journal of Communication Society. It is open source, so if you are interested in having a deeper look at this, you can do so by following the link on the slide. In this way, we conclude the presentation. If you have any questions, feel free to contact me.